Stanford University.
All right, last time I started to tell you something about how quantum field theory gives rise to a theory of the particle interactions through an object called the Lagrangian. I think that was not terribly clear, so I want to go back to it a little bit before starting to discuss the details of particle physics. We're still thinking about quantum field theory. The basic technique that I was alluding to last time is called the path integral method of quantum mechanics. And it is the most direct route to Feynman diagrams, to the theory of particle interactions that are based on Feynman diagrams. So let me just try to briefly go through the basic ideas, which we started to do last time, but I don't think I was sufficiently clear. Anyway, the path integral formalism or method in quantum mechanics due to Feynman is a generalization, is the quantum mechanical version of the principle of least action. So I just want to remind you what the principle of least action is. If we're talking about a particle, now I don't mean a particle from the particle physics quantum field theory point of view, just a classical Newtonian particle, the motion of a classical Newtonian particle from one point of space-time to another, just very quickly, is determined by a Lagrangian. Lagrangian is a function of the coordinates of the particle, the time derivatives of the particle, and from the Lagrangian, whatever the Lagrangian is, one constructs the action. And the action is an integral along the trajectory of the particle of the Lagrangian. For every trajectory, whether it's the true trajectory or not the true trajectory from here to here, by the true trajectory, I mean the solution of Newton's equations from one space-time point to another space-time point, whether or not the trajectory is a solution, it has an action, the integral of the Lagrangian along the orbit. The classical principle of least action is that the trajectory followed by the particle through space-time minimizes the action. From that, you can derive differential equations, and those differential equations are called Newton's equations. And I will assume that you know a little bit about this idea of action. Now, the same idea applies to classical field theory. And the way the idea works is for a particle, for an ordinary particle motion, the Lagrangian is a function along an orbit, a function of an orbit. For a field theory, and of course it's an orbit which connects some initial configuration to a final configuration. For a field theory, the equations of motion of a field theory, classical equations of motion, are also determined from a Lagrangian. The Lagrangian is a function of whatever fields, I'll call them generically just phi, and not just the time derivatives of the fields, but the space derivatives and the time derivatives. Let's say derivative of phi with respect to x mu. That's just a shorthand way of saying that the Lagrangian depends on phi and derivatives of phi. One thing which is required by the theory of relativity is that the Lagrangian be a scalar, that it transform under Lorentz transformations as a scalar. But that being said, the Lagrangian can be anything built out of phi's and derivatives of phi. Okay. What is the action? Imagine we have a region of space-time. Time, as usual, flows upward. Space is horizontal. And we have a region of space-time between an initial time and a final time. Okay. Then the action in this region, the action is the action in this region, just as the action for a particle trajectory is the action from one end point of the trajectory to another. Here it's the action in a region of space between an initial configuration and a final configuration. And the action is equal to the integral over that region. Let's write a d4x, which means the time and dx and dy and dz of this Lagrangian. So it's the total integrated value of the Lagrangian over space and time, whereas for the particle it's just an integral over time. Now what do? What's the analog of a starting point for the particle? A value of the field on the initial surface here. Given not just one field, but all the fields in the problem, prescribing the values of the field on the initial surface here, and prescribing the values of the fields on the final surface, you can ask, is there a solution of the equations of, let me go back a step, forget that. Yes, is there a solution of whatever the equations of the theory are, which starts with a given initial value of the fields at time t equals 0, let's say, and ends with the fields being something different at some later time? And the answer is the principle of least action again. The equations of the theory are formulated by saying, yes, there always doesn't exist something in between, which is a correct solution of the theory, which has a given initial value of the fields here and a given value of the fields at the end point, and the correct solution of the fields in here is the one which minimizes this action, one which minimizes the action. So the principle of least action gets extended to a kind of space-time principle of least action, where the degrees of freedom in here are fields. Okay, now let me very quickly remind you what the quantum mechanical use of action is, how exactly you derive the classical principle of least action from the quantum mechanical version of Feynman's quantum mechanical version. We don't really need to get into here. You can go look it up and anything about path integrals. But for a particle, let's come back to the particle motion for a moment. According to Feynman, or according to quantum mechanics, a thing that you might want to calculate is the amplitude.
Is there anything wrong with the value of a field returning to itself?
No. No more than the possibility of the position of this thing returning to itself.
So how do you go from one space-time event to another space-time event?
Why space-time events? We're having values of fields here and values of fields here.
Well, we're integrating d4x, so there has to be some d4 trajectory.
No, the trajectory is replaced by a history of the field from the beginning to the end. A history means the values of the fields all along here. Everywhere is in here. Okay? The idea of a trajectory becomes a trajectory in field space, which means
we have to specify actually the coordinates as well as the field values to get an initial point.
to get an initial point.
Well, you're specifying the initial boundary condition or whatever as field values.
Field values all along some initial surface. You pick the initial surface.
Right. Okay, so
In other words, you pick time.
the whole field at some cross section.
It's the whole field along some cross-sectional. Yeah. All right, which is another way of saying the whole field at a given instant of time. And the final configuration is the whole field at some later time. And the question is there a solution of the theory, whatever the theory is, which interpolates in between these in the same way that a trajectory interpolates from here to here? And the rule is minimize the action. That, if carried out, we did this a number of classes ago, but if that's carried out, the requirement of minimizing the action leads to partial differential equations for the fields, and those partial differential equations are things like Maxwell's equations, things like Einstein's equations, and so forth. All right, so let's come back now to the quantum mechanical idea. The quantum mechanical idea has to do with amplitudes. Amplitudes are things out of which you construct probabilities. So for example, you can ask the question, what is the amplitude that if a particle is injected into the world, however it's injected in, at a space-time point x and t, what is the amplitude that if I look for it at a later time, let's say this is at x and time t, what's the amplitude that if I look at a later time, let's call it t prime, that I will find it at position x prime and t prime? So it's the amplitude that if I start a particle at this point, close my eyes for a while, and then turn on a detector which looks for the particle at a certain place, the amplitude for finding it there. That amplitude is a complex number that depends on the initial point, on the final point. It's a complex number whose magnitude squared is the probability. All right, that's the rule. Square the amplitude or multiply it by its complex conjugate, and that is the probability for the particle to go from here to here. Feynman's rule is the following. It says, take the action for any trajectory, take an arbitrary trajectory, and write down the expression e to the I minus I, the action of the trajectory. We can just write it out. It's integral of, now we're talking about particles now, integral of the Lagrangian dt from one point to another point. It's a function of, or functional of the trajectory. And now, actually there's a factor of h bar in here, a factor of h bar in here. That's where quantum mechanics comes into it. Sum this, or integrate it, over all possible trajectories. Well, in non-relativistic quantum mechanics, you don't let them go backward in time. But all possible trajectories which never loop back on themselves in time, sum that over all the possible trajectories. For each trajectory, it's a complex number. Add them all up. Now, how do you add up such a thing? It's some complicated kind of integral. But we needn't worry too much about the details of how you actually calculate it. That, according to Feynman, is the amplitude for going from here to here. It's the sum over all possible classical roots. Classical root does not mean a solution of the equations. It just means a possible root. It's the sum over all possible roots, whether or not they're solutions of the equations, of Newton's equations, of e to the minus I times the action, measured in Planck's constant units. Incidentally, Planck's constant has units of action. So this is simply the action in units of the Planck's constant.
The E arises because to go a little step involves something very one plus an term in the action, and you have to multiply these all together.
Right, exactly. That's exactly right. And the other thing here is the I. The I is part of quantum mechanics, what can I say? Yeah.
That sum is the probability?
That sum is the thing whose square is the probability. By square, I mean times its complex conjugate. This sum could hardly be a probability because in general it's complex. It's got an I in it. If you multiply it by its complex conjugate, that is the probability. This is the probability amplitude, the complex thing. All right. So this is Feynman's formulation of quantum mechanics, and now it can be extended to quantum field theory. In quantum field theory, the corresponding question, now we're not actually going to formulate it this way because, but this is a correct way to formulate it. We're going to fudge it a little bit and make our way through it without any rigor. But the same idea. You start with an arbitrary configuration of the field. All right? So that's some initial phi of x, x now being just x and not t. An initial configuration of the field. And now you look at some final configuration of the field. Let's call it phi prime of x. And these are two different functions, And you can ask, what is the probability amplitude that if I start the field at some value and let the system go and then detect the field at a later time? Imagine you had some way of starting an initial condition with a field being prescribed at every point of space. Of course, that's an idealization. You don't have a chance in the world of doing that really. But you had some sort of apparatus which allowed you to start the field in an arbitrary configuration, let it go, and then you had another apparatus which detects the values of the field at every point. Then you can ask, what is the probability that if you start the field in a given way, that at a later time the field will have some value? Again, that probability is determined in terms of a probability amplitude, and the probability amplitude is, again, the sum over all possible ways of interpolating the field between initial and final, all possible, exactly what I said, all possible ways of filling in between the initial state and the final state with a field value at every point of e to the minus I h times the field action. That's the integral dt, dx, dy, dz, d4x of the Lagrangian, which is a function of phi and the derivatives of phi. So you evaluate the Lagrangian at every point, integrate it up. That gives you the action for a particular, let's call it a trajectory. It's not really a trajectory in any ordinary sense, but it's a history. Let's call it a history, better yet. For each history, each possible history that you can imagine, it doesn't have to be a true history, a real history. For every possible history you can imagine, there is an action. The action is itself an integral. But then you can sum this over all possible histories, and that is the amplitude to start with a field value phi and end with a field value phi prime between these two trajectories here. Okay? That's the notion of a path integral. Yeah.
I'm not concerned that there are an infinite number. I'm not concerned that there are an infinite number of paths, but the action is going to be a finite number for each of these paths.
Yeah.
So that,
Well, it's a finite complex number, right?
yeah. So how can that converge to anything? Why is that not a infinite number?
No, there are many, many integrals. Well, okay, you're asking. All right, let me phrase it. Let me phrase it a little more strongly. Adding up an infinite number of numbers. Well, that's nothing special. I think what you're pointing out is that each one of these numbers is not only finite, but has a magnitude equal to 1.
Or something that is not decreasing.
It has a magnitude equal to 1. Right? It's an exponential of I times something, right? So any number like this is a number which on the complex plane, not minimizing it, you're summing over all trajectories.
You're just summing over all of these amplitudes, okay.
Now, these things do converge. They don't. They converge because they oscillate. They all lie on the unit circle, not on the infinite circle, on the unit circle, and yet the integrals do converge.
That's the definition of delta function.
For example, that's one example, but there are many examples where integrals like this converge. The kind of thing that can't converge, well, if you have an infinite number of numbers, all of which are positive, and you add them up, positive and bounded away from 0, right? You have an infinite number of numbers, all of them positive and bounded away from 0, of course that's going to diverge. Okay? In this case, you have numbers which can cancel. Over here is one trajectory, over here is another trajectory, over here is another trajectory. These are the amplitudes for different trajectories. And this one cancels this one. So it's not hard for an integral
Well, you
where
could say
the-
if they're equally distributed around the unit circle, then you get.
0.
Yeah.
And in fact, most of them, except for a small fraction of them, they are.
That's right. They tend to cancel a lot. The only trajectories which tend not to cancel are the ones near the classical trajectory. We don't have to discuss that now, but that is the way that you go from quantum mechanics to classical theory, at least in this formulation. If you look for the particular trajectories where you have the least cancellation, those are the trajectories of stationary action, the trajectories where the action is minimum. But that's another story. This is the quantum mechanical path integral formulation that much of modern field theory, basically all of modern field theory, quantum field theory, is based on. All right, now I'm not going to derive the next step. I'm simply going to state the next step, but I wanted to at least explain to you what this quantity is before I show you how in practice it's used. Now, when I say in practice, this is a bit of an oversimplification, but not too bad, not too bad. The last time we talked a little bit about how the Lagrangian is used to calculate processes, particles moving from one place to another, particles interacting. When I say calculate processes, what did I really mean? I really meant calculate the probability for an initial state to go to a final state. But there are two distinct ways to think about about quantum field theory. One is in terms of fields and the other is in terms of particles. We know that there is this duality between particles and fields. We could ask a apparently totally different question. Instead of asking, suppose you had a given field value here and you want to know what the amplitude is for a final field value, we could ask, supposing you had some incoming particles, quanta of the field. You express things in terms of field quanta rather than in terms of classical field configurations. Supposing I told you that the field initially was in a state which was described by a particular collection of incoming particles. Incidentally, when I say the field, I may mean a collection of fields. All right, so I tell you not the value of the field along here, but rather the particle content coming in. And I tell you what the particle content is going out. And I ask you, what's the probability that you went from one particle content to another particle content? It's a question of a similar kind of question, but expressed in terms of the particle representation of quantum field theory rather than the classical field configuration. And the answer, not surprisingly, involves exactly this same object. Okay? We talked about it a little bit. I think what I told you last time was not incorrect, but it was a real small piece of it. I said what you do is you took one, I'll just remind you of something I said, and then I'm going to say it again, but in a more correct way. You take 1 plus the Lagrangian. Remember what we did. We said, let's divide up into space-time into lots of little cells. It's hard to give meaning to objects like this path integral, directly. The way to give meaning to it is to divide up space into lots of little cells, and instead of thinking about continuous functions or even discontinuous functions, think about a value of the field in each one of these cells. All right. That makes it more concrete, and then in the end, you let the size of the cells go to 0. So let's not let the size of the cells go to 0. Let's keep them finite like this. What I told you is that you take the quantity 1 plus the Lagrangian in each cell, in the ith cell, call it L sub I. That's the value of the Lagrangian in each cell, and you multiply it for all the cells. Remember I said that? If you don't, it doesn't matter because we're going to say it again the right way this time. Right? And then we did something with this to try to calculate, and I tried to show you that there are pieces in here which describe the propagation of particles, the collisions of particles. We're going to go back over it again, because it really is central. All right. First of all, I missed being tired. I was not terribly clear. It's really 1 minus I times the Lagrangian in each cell. Okay. All right. Now 1 minus I, 1 plus a small, this is, for the moment, imagine, this is a small quantity. I shouldn't, actually, it's not 1 plus the Lagrangian. It's 1 plus the action in each cell. Now, the action in each cell is the Lagrangian times the times the space-time volume in each cell. All right? Space-time volume is delta x, delta y, delta z times delta t for each cell. Let's call that a small number. Let's just call it the space-time volume. Let's call it a to the 4th, where a is a small number. All right, so each little cell is small, so the action in each cell is itself small, right? Because the cell is small. Now, 1 minus or 1 plus a small quantity, let's call it 1 plus epsilon, is an approximation to e to the epsilon. E to the epsilon is, this is approximately equal for small epsilon. But the exact formula is a power series in epsilon. It's 1 plus epsilon squared over 2 plus epsilon cubed over, what comes next? 3 factorial, which is 6. 3 times 2 times 1. And so forth and so on. So 1 plus epsilon is approximately, for small things, equal to e to the epsilon. But in fact, it's more efficient and correct to really write something different than what I wrote over here, namely this thing. Let's think about what this thing is.
In fact, don't you have to put an H bar in a...
Here?
Yeah.
Yeah. All right, I'll probably wind up setting h bar equal to 1 as usual, but right. Okay, what is this object? All right. This exponential here, what's in here, we're going to imagine replacing not by an integral but by a sum. The integral over space and time here, just imagine that we've replaced it by the sum. And what is it a sum of? It's the sum of the action in every little cell, right? When I replace the sum of the integral by a sum up in here, when I replace the integral by a sum up in here, what I'm really doing is just adding up the action in all these little cells. Now, the thing about a exponential is that the exponential of a sum is the product of exponentials. E to the a plus b is e to the a times e to the b. So this can also be written as another way. In another way, forget the summation here for a minute, that's summing over paths. Before we do that summing over histories, what this object is, it's an exponential of a sum, so it's also the product of e to the minus I over h bar, a in the first cell, e to the minus I over h bar, action in the second cell, a is action, e to the minus I over h bar, a in the third cell. And it's exactly this kind of product product over all the cells, not of 1 minus I times the action, but of e to the minus I times the action. They're close to each other. It actually wouldn't matter which we used, but in practice. But okay, so let's now consider. Question? Okay. All right, so now having this form here, let's go back to let's forget particles for a minute and think about fields and re-express the path integral idea. So here we have a region of space-time that's been chopped up into tiny little cells. Enough. All right, what's the idea of an initial condition? The idea of an initial condition is to start on the first row of cells here and give the value of the fields at every point in there. That's an initial condition, or that's the analog of an initial condition. A final condition is to specify the fields in the last row. So the question then is, what is the probability amplitude that if the field is specified in a certain way on the first row, and the field is specified in the last row, what's the probability to go from one to another, or the amplitude that if you started a certain way and let the system run, you will later find it in the final state. And the final state now means the field in each one of these cells here. Answer, you take e to the minus I times the sum of the action in all the cells, but we now realize that this is simply the product of e to the minus I of the action in each cell. We multiply together the action in all of these cells for a given history, which means a given value of the fields in each cell. And we multiply them all together. We compute the exponential of the action, and then we sum it over all ways of populating the cells with fields. All possible histories means all possible values of the fields that could be in every cell, with the exception of the first row and the last row. The first row and the last row are fixed by the initial and final conditions. All right, in other words, by the initial and final conditions. We don't look at the field in the interior. We simply start the system and then detect it. And the rule is sum over all possible field configurations that could exist in between. So that has reduced this idea to a discrete form in which we see that what we have here is this infinite product, or this product over actions. All right, now let's try to formulate some ideas about particles. Instead of asking the question, what if we start with a given field configuration? What if we start with a given particle configuration and end with a given particle configuration? What is the amplitude to go from one to the other? So I'll tell you how you think about it. We're not going to derive this. We've talked about it a good deal. We've talked about the ideas a good deal. We've talked about the fact that fields are made up of creation and annihilation operators. And what we're multiplying together here is functions of the fields. Functions of the fields, and therefore functions, yeah.
I read somewhere that someone thinks that field quanta are not necessarily identified with particles.
You're right.
You would disagree with that?
Well, I'm not sure who and what was the context.
Field theory.
No, I'm not sure who said it and what the context was.
But you
Well, give me a little more to go on. The question was, somebody said something. All right, my grandmother probably said it, but
that the field quanta in quantum field theory are not necessarily identifiable as a particle.
the only thing I can think of is that he was talking about quarks. And of course, in some sense, quarks are particles, but in some other sense, they're never detectable as particles because they can never escape from one another. That's the only thing I can think of. So quarks are the quanta of the quark field, but they're never directly detected as separate quarks, well separated from other quarks. That's the only thing I can think of that he might be speaking about.
Well, I guess during unitary evolution, it doesn't necessarily boil down to observables, and so you may not have particles that are identifiable at intermediate states.
I don't know what the... if you accept the idea of a quark as a particle, it's true that there's not a one-to-one correspondence necessarily between the fields in a theory and the particles in the theory. That's an idea which is true as long as the coupling constants in the theory are small. Okay, so there is not necessarily a one-to-one correspondence. Yeah, I mean, it is true. There are field theories that, for one reason or another, you wouldn't describe their quanta as conventional particles. But, you know, at some level, it's just a difference between words. If you define particle to mean quanta, then there's no difference between them. They're indivisible. They carry energy and so forth. So for my money, I would call them particles. But yeah.
When you talk about summing over histories, is there some limitation on what histories you talk about? Do they have to be sort of continuous in some sense?
No. In fact, they don't have to be continuous. First of all, of course, the idea of continuity on a discrete space like this doesn't quite mean very much. The field in the neighboring cell is just going to be a different value of the field. The rule is divide the space into cells, and in actual practice, this is the way quantum field theory is defined. You divide the theory into cells, you sum over all possible ways of populating the cells with values of the fields, all possible ways. No restriction to things which are approximately continuous. And in fact, quantum fields are not approximately continuous. They jiggle a great deal. And you sum over all the possible values of the fields, and that gives you your answer.
So in principle, for each field and each derivative, you can assign it all possible values from minus infinity to plus.
Well, you don't assign the derivatives separately from the fields. The derivatives, of course, are related to differences of the fields in neighboring boxes. Okay. So you populate with field values, and then derivatives are replaced by, yeah. And you can use, there are different rules that you might adopt. You might define the derivative here to be the difference of the field here and here. Right. Yeah, that's a minor detail, and
yeah. But in any event, you might take the real line up and break it up into small intervals, but you'd still have a sum over a countable number of possible values of the field for each field, and if there were two fields, then you'd be doing that over.
Yep. By the field here, I mean all of the fields. Right, so you would give a value to each possible field in the theory at each initial
state. It's a really
state.
nasty-looking computation.
Absolutely.
Well, so since these are complex functions, they're analytic functions, so...
Well, they're analytic functions of
But the relationships between the values of the field have to conform to, you know, what you learn in complex variables, you know.
No, complex variables is about the theory of analytic functions. Analytic functions are extremely smooth. They're the smoothest functions you can think of. These functions do not have to be smooth. They're complex valued, but they're not analytic functions. The fields as functions of position? Definitely not. They're on the average, highly discontinuous, but
If I were to do the if I were to do the computation on computer, how do I know?
they will converge and do all the right things.
Yeah, I mean, how many different fields I have to consider?
How many different?
Different assignments I have to
Okay.
consider.
So, of course, this by now is a major industry called lattice gauge theory or lattice quantum field theory. Lattice because it divides the world into a lattice. And this has been studied to death, how to do these integrals in practice. By now, it is a very effective tool, but it took, some 30 years to develop the computing technology. I was involved in it in the very, very beginning, very beginning. I wasn't involved in the computer technology of it, but setting up the rules for lattice gauge theory. Okay, so there was a history. The first part of it was setting up the rules for it, and that took about 3 weeks, and then something like 30 years to develop the technology to compute these things. And you're right. I mean, how do you know when you've sampled enough of the space? Okay, so there are, and a lot of the wisdom of it came from statistical mechanics, where you do very much the same thing. You calculate partition functions or probability distributions for this checkerboard here. Not of quantum field theory. It could be a real crystal lattice. And you might be summing over configurations of whether there is or isn't an electron in at each site. So a lot of the methodology came from the quantitative study of statistical mechanics systems. We have the same question: how do you know when you've sampled enough? And this is not the subject of tonight's lecture. So the answer is. The experts know, or they think they know, and they get good answers. They get good answers which agree with experiments. So it seems to work. Okay, so let's go back and remember that quantum fields are a shorthand for creation and annihilation operators. And if we're talking about, let's say, the product of some fields in this box times the fields in this box, that can represent the annihilation of a particle in this box and the creation of a particle in a neighboring box. So we might just represent it by a particle moving from one box to another. Okay. What kind of things in the action here actually do correspond to a particle moving from one box to another? So let me tell you. There are things in the action here which, strictly speaking, are not associated with one box but with a pair of boxes, namely the derivative terms. The derivative terms, I was a little bit hasty here when I said you multiply all these things together, one for each box. That's a little bit of a cheat, because there are terms in Lagrangian which are associated with pairs of boxes. So really you can think of it as summing over the boxes and summing over neighboring pairs of boxes, but that's a detail. Which terms involve pairs of boxes? The terms which involve pairs of boxes are things like the derivative of phi with respect to t squared. The derivative of phi on a lattice becomes the difference of phi in neighboring boxes. So in here, this derivative of phi with respect to t might really be written as phi at point x, well, phi at point t and x minus phi at point neighboring time and x.
Do we actually have second derivatives?
No second derivatives. These are first derivatives.
I mean, would we?
Never.
Okay.
Never. Bad idea. Does real damage. Now, what about derivatives with respect to spatial coordinates? Same thing. It corresponds to the difference two neighboring points in space. And then the instruction is to take 1/2 of the square of the derivative. Well, 1/2 of the square of the derivative will have in it, I just want to focus now on the terms which multiply phi times phi at a neighboring point. Let me just focus on those. There's also terms in here which multiply by phi by the value at the same point, but in particular, there are terms in this Lagrangian which multiply phi at one point times phi at a neighboring point. Every time you lay down a term like this, it represents the motion of a particle from here to here. You can think of it that way. Okay, let's concentrate on these terms. Let's forget the interactions in the Lagrangian. These are called the kinetic terms, the quadratic terms in the Lagrangian. They're things which are easy to deal with, and they do correspond to motion of the particle from one point to another. Let's look at this, and let's include only those. We don't even need to write it in this form. Let's just write it as e to the minus I times the sum over all pairs of boxes, over all neighboring pairs of boxes. I said over all boxes, but it's clear that's not quite right. We want to think of it as sums over neighboring pairs of boxes of things like phi in one box times phi in a neighboring box. I'll use the notation x and x prime to represent neighbors on the lattice. That's what goes into the action, or that's what goes into the exponential of the action. There are some coefficients in front of it, of course, but that's of secondary importance. And now we can expand out this exponential. Let's see what's there. There's 1 minus I times the sum of phi of x prime. And then things like, let's see, what's the next term? I times I is minus 1, so it looks like it's minus summation of phi of x prime squared times another factor of the sum of phi of x prime. Or this could be phi of x prime, x double prime, x triple prime. X double prime and x triple prime are one pair of neighbors. This is another pair of neighbors, and I think I left out a factor. There should be a 2 factorial downstairs. I'm simply expanding out the exponential here. And what's the next one? Well, it has 3 powers of the sum, 4 powers of the sum, and so forth. Okay? Let's look at each term here. The first term has something which involves a sum over the lattice of an annihilation of a particle at one point and a creation of a particle at another point, okay, at a neighboring point. The next term, incidentally, the rule that I'm going to tell you, again, I'm in the business of telling you some rules now. I'm going to tell you some rules now. The amplitude for going from one thing to another, the rule is you've got to close off. You must not have a dangling endpoint. A dangling endpoint can only dangle like that if you've got an operation to put a particle into the system. A dangling endpoint, for example, we're going to have diagrams which have particles going from one point to another. If they end like this, they're illegal unless there's an instruction to put a particle in at this point and to take a particle out at that point. So endpoints like this, we will simply rule out as things unless they correspond to a specific instruction to put a particle in at this point and take it out. Since we're only putting particles in the initial state and taking them out in the final state, the only endpoints would be allowed on the top and the bottom. Okay, so let's take a particular term here, phi of x and phi of x prime. These are neighboring points on the lattice, and they correspond to a motion of a particle from one place to another. There's a sum of terms. There could be a term for a particle from here to here, a term for a particle from here to here, a term for a particle from here to here. But none of these will contribute unless, of course, there would be one situation in which they would contribute. That would be, of course, if this layered structure here was only 2 layers high, and we put in a particle over here and took one out at the neighboring point. Then there would be a contribution to the amplitude of that coming from this term in the product, phi of x times phi of neighboring x. That would contribute, and it would contribute to the amplitude, basically the factor minus I. It would tell you that the amplitude to go from one point to another was simply minus I, this coefficient here. Okay, but that's not very good if this how do we get from here to here? Okay, from here to here. How do we get a particle from here to here and calculate the amplitude that if we put in a particle over here, that will detect it over here? For that, we have to find in this sum of products here, we have to have a term which will leave no dangling ends. Okay, let's just take this term here. Right. This has a particle moving from x to x prime, and then another particle moving from x double prime to x triple prime.
Are you saying the second term contributes only if only when the initial and final state are adjacent?
This term here, yeah. Yeah, that's right. This notation means neighboring particles, neighboring boxes. Right? Here we have one neighboring box, and here we have 2 other neighboring boxes. Yeah.
On that one, you have the 5x prime. The first term is 5x prime.
Yeah.
And the second term is 5 double prime.
Yeah, it just means pick 2 neighboring and sum over all possibilities. This is a sum over all neighboring pairs.
So it doesn't have to be adjacent to the first.
No, in general not, but it can be. In fact, this could even be the same pair, but it doesn't have to be. Sum over all of them. All right, so what does this one do? It moves a particle from x to x prime, and this one moves a particle from x double prime to x triple prime. Right? So one of them moves a particle from here to here. This is x prime to x double, from x to x prime. And then the other one moves a particle from here to here. That's x double prime and x triple prime, let's say. Obviously, there's going to be dangling ends unless, well, let's take this case here where we only have 3 layers. If we only have 3 layers, the only way to avoid dangling ends is to have the first particle connected to the second particle, the first box connected to the neighboring box, and then this box connected to this box. There won't be any dangling ends except for the dangling ends which correspond to the initial particle and the final particles. Right. So if this was only 3 layers thick, we would find a contribution here, namely where x prime is the same as x double prime, that transports the particle from the initial position to the intermediate position, and then from the intermediate position to the final position. Okay. What would be the amplitude then associated with a particle going from here to here? At least corresponding to this term, it would be a 1/2 factorial and a minus sign. That would be it. You read off the coefficients, and the coefficients tell you the amplitude. Thus far, we don't have a way to get from here to here. Not with 2 steps, anyway. 2 steps can... However, if this was only 2 layers thick, we would have now a way to get from here to here, to go across the diagonal. How do we go across the diagonal? We go again to this second order term here, the term which has a 2 factorial in it, and we find the term which takes us from x to x prime, and then from x prime, from x to x prime, and then from x prime to, from here to here, and then here to here. All right. What's that?
There are other paths,
There are other?
other paths to get to this answer.
Yeah, there's another path where you jump from here first to here and then up. I don't think there's any other besides that. Yeah, not with not with just 2 terms, right. Okay, but now there was no reason to stop here with only 2 terms. Let's go on. We can have 3 terms. 3 terms would correspond to going from one box to an adjacent box. Well, it would correspond to 3 distinct steps. And if those 3 distinct steps were connected together into a chain, in other words, in this sum of products, we found the term which took us, yeah, we could come right back again. That would contribute, together with the direct jump from here to here, would contribute to the amplitude to go from this point to this point. So you see, built into this prescription is something like the original particle path integral idea. The amplitude to get from here to here is the sum over the amplitude to go from here to here, and the amplitude to go through another route, also this one back here. And eventually, if you expand this out to arbitrary order, there will be a term in there for every possible route that you can take to go from any initial configuration to any final configuration of that particle. So, first of all, just thinking about a single particle moving in space-time, this field Lagrangian contains information about the amplitudes to go from, now let's take an arbitrary, to go from any point to any other point. What you do is you add up all of the possible ways of going there, and what is the coefficient for each way of going there? You read it off the coefficient that multiplies that particular term in this sum. 1 over 2 factorial, 1 over 3 factorial. Some of them have i's, some of them don't have i's. Remember that I squared is -1, so some of them have i's and some of them don't have i's. And so in general, the amplitude to go from one point will be a complex number.
But they can also go back and forth.
That's what's new. That's one of the things that's new here, that they can propagate up and down, and that's a feature of relativity.
Even the same 2 cells,
What's that?
even the same 2
Oh, yeah.
cells thousands of times.
Oh, indeed. Yeah. Yeah. All right, let's talk about going backward in time. You could think of, here's one that goes backward in time. You can think of this as either allowing a new rule where particles can go backward in time, or you can follow time forward and say what really happened here is the particle moved from here to here, and then a particle pair, particle and antiparticle in fact, were created, the particle half of it going to here, and the antiparticle combining together with the original particle to annihilate. Think of it either way. But the rule now allows trajectories which go backward. Let's come back to this term here.
formulation, since you have n factorial in the denominator, does this mean that you sort of have convergence in the normal sense of convergence?
Well, the n factorials certainly help the convergence, but they're not enough to make it converge.
E to the I something.
Hmm?
Of course, this is just an expansion
Yeah.
of e to the I
That's
something
right.
or other, so of course it converges. You have a
No, 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 but the sum over configurations doesn't have to converge.
Well,
Yeah, this part converges, yeah.
right.
That's right.
And this is going to be some finite number of total configurations considered.
Yeah. Okay, all right, now let's go on to a slightly different problem. We studied the particle moving from one point to another. Now let's suppose we put in two particles, and we want to know what the probability for the two particles to go to two other particles is. In other words, we want to start, and I'm going to take the case where there are only two layers for a moment. There's the case with only two layers for a moment. And I want to know the probability that if I start a particle over here, it will get to here. No, if I start two particles, one over here and one over here, that they'll get to here. Okay? Well, come back to this term. Now remember what this term did for me before. Before, it allowed me to hop 3 units. But that same term allows two particles each to go 1 unit. Look at it. This can create a particle. This can annihilate it. This can create a different particle and annihilate it. This corresponds to a graph where you start a particle in here and goes to here. That's this factor. And the other factor, instead of taking the particle that's already there and moving it over here, it just takes a totally new particle and moves it to here. Okay? So this same factor, the same term, contributes both to the motion of a single particle, 3 boxes, and it contributes to 2 particles, each moving 1 box. Did I say that right? Yeah, more or less. 3 boxes, 2 boxes. Yeah. So there's a lot in here besides just motion of a particle from one place to another. It has information in it about any number of starting particles going to any other number of final particles. Now, in fact, particle number doesn't change as long as we just take this into account. Why not? Because every dangling endpoint here, well, let's see. Yeah, it has to end somewhere, but
Well, if you start and end with different numbers of particles, then obviously something has to happen.
well, that would mean there has to be a dangling in somewhere. Supposing I wanted to, I mean, I can't, how would you get from one particle to 2 particles?
What if I start with electron and positron? I could end up with no particles.
Well, okay, that would be something, all right, that would just be something like this. 2 particles, let's put another layer in here. Yeah. Yes, that's true. That would correspond to an electron and a positron, for example, annihilating each other. The only problem with it is it doesn't conserve energy. So in fact, when you added up all these amplitudes, you would get 0. But
So you have to
yeah. But but under certain circumstances, if there was an electromagnetic field to soak up the energy, yes, you're right. It would have information in it about an electron and a positron annihilating. Right. So there's just a lot in here. There's a lot in here, but not everything. Not everything. To find out the other things that are implicit in the field theory, there are other terms in the Lagrangian. Now, what you put in the Lagrangian is determined by experiments, and it's really just a way of codifying the results of experiments. But what else can you have in Lagrangian? We had the derivative terms, let's say phi dot squared minus the derivative of phi with respect to x squared and y squared and z squared, all that kind of stuff. That was the stuff that I wrote down as phi at one point times phi at another point, at a neighboring point. Then there are possibly other things that just involve phi and not its derivative. So, for example, you could have things like phi squared. Do you remember what the coefficient is? There's usually a 1/2 here. That's a convention. Remember what the coefficient of phi squared is? The square of the mass of the particle. We should divide by 2. That's, again, a convention. And if we included this term here, what that would do, it doesn't move a particle from one place to another. It absorbs a particle at one point and emits it from the same point. Right? From the same point. So it would correspond to graphical constructions where we would add a new rule. If a particle enters a region here, from one box to another, one of the terms that can act is this mass squared term. It would simply take the particle and do nothing to it. It would leave it in the same spot. Then another term could come and move it, but it would weigh that particular path with a factor of m squared. Every time this term acts, it weighs the path with another factor of m squared in the amplitude. So there would be terms where no m squares act, where only these derivative terms act. In other words, where in expanding this product out, we only had the derivative terms. That would be the theory of massless particles. The theory of massive particles would have a new rule that one of the possible things that can happen at every step is you may or may not just weigh that path at that point with the m squared. All right, so the mass term is another rule for how you evaluate these paths, these path integrals. Another rule. It's, we don't have to get into detail. The main point is that the mass of a particle is codified by another term in the Lagrangian, which is m squared phi squared, which weighs paths in such a way that it knows about their mass. All right, but more interesting is the more complicated terms, things like phi squared. Let's put a phi cubed. Phi cubed can do a number of things. It can annihilate one particle and create two particles. It can annihilate two particles and create one particle. It can create three particles. It can annihilate three particles. All right, so that's a new kind of thing that can happen on this checkerboard here. In expanding out the action, expanding out the exponential, there might be additional terms here, for example, g phi cubed. When we expand out, we can have not only these products which take a particle from one point to another, but also processes where particles are created and annihilated in threes, either 2 in, 1 out, 2 out, 1 in, or 3 in or 3 out. What that looks like on here is, for example, supposing we have several of these quadratic terms which move particles and one cubic term. What can that look like? Well, what it can do is it can take a particle, moving it from here to here, and suddenly in that box we put a phi cubed. In that box, it can absorb one particle and emit two more. Now, the next thing that could happen is the two particles could move to other boxes. But basically what it does is it takes a particle, absorbs it, and creates two. And those two particles can be on their way. And this would then contribute to a process where one particle came in, two particles went out. In fact, you can make very, very complicated things. You can make things of let's go back to the one particle going from one place to another. one particle going from one place to another. Let me stop drawing checkerboards. Let's just imagine the checkerboard there. One particle go from one place to another can go directly, just a bunch of small hops, a bunch of these hops. But also something else can happen. On the way, at some point, the cubic term could act. If the cubic term can act, it can take that one particle coming in and split it. Split it into two. And then both particles move along until another cubic term, something quadratic in the cubic term, something with two cubic terms in them, can create an extra particle and reabsorb it. So in fact, the actual amplitude to go from one point to another by one particle is not just the sum of simple trajectories going from one point to another through the space-time, but is more complicated. It has infinitely more complicated. It has processes where the particle splits and rejoins. In other words, where the particle emits a second particle, which is then reabsorbed. An example of this would be an electron moving along and emitting a photon and reabsorbing it. Part of the amplitude for an electron to go from one place to another is through the process of emission and absorption of a photon. It can get wildly more complicated. Of course, we have to add all of these up. The rule is add up the amplitude for every possible way to go from the initial state to the final state. Right? You could have several of these splitting and joinings. You could have things jumping across the gap between particles. And this can get arbitrarily complicated from the point of view of electrons and photons. Things like this could happen. You know, electron goes through, photon emitted, another photon emitted. But even worse, the photon can break up into an electron and a positron. But then the electron and positron can exchange a photon between them. All of these processes come out of expanding out the action like this and finding the individual terms which do all of these things. If you want the amplitude for any one of these processes, you just go back to what appears here, find the term that you're looking for, and find the coefficient in front of it. It may or may not have an I, depending on whether it's an even power or an odd power, and it will have some factorials and so forth. That will give you the amplitude for a specific process. But then the full amplitude to go from one thing to another is the horrendously complicated sum of all these things.
Right, so you may have certain things that happen in multiple of those histories.
And what?
In multiple of those histories, you may have similar terms, which then the overall amplitude for that process would be actually from all the different histories.
Yeah, from all the different histories, going from the initial to the final. So there are two ways to think about field theory. One is to think about fields and think about histories as initial values of the fields, final values of the fields, and you sum over all the values of the fields in between. And the other is this particle way to think about it, where the field is replaced by a distribution of quanta. And again, amplitudes for initial configurations, which means an initial particular set of particles and a final set of particles. The basic processes, the basic underlying processes which happen are governed by this Lagrangian. That is the most important thing. Anytime you have more than two fields interacting, you have an interesting interaction process where particles can split and join and so forth. What would happen if you had 5 to the 4th here, which is a perfectly good interaction? That would be some place where a particle, for example, could come in and break up into 3 other particles. You know, 1 to absorb the initial state, 3 to emit the final state. Or it could be a scattering in which 2 particles come along collide, and 2 go off. Anything that looks like a vertex with 4 particles all together, 2 in and 2 out, or 2 in, or 3 in, 1 out, or so forth, or just 4 out, or 4 in, they're all governed by this term. And so forth and so on. Let's see, how are we doing?
So that's the spontaneous arrival of 4 particles at the final state?
Yeah, except once again, it would violate energy conservation. So if you really worked it out and added up the amplitude from every position where this could happen, every space-time position where it could happen, you would find out that, that it doesn't happen. It doesn't happen. In other words, they all add up to 0. Okay, so processes which violate energy typically all add up to 0 in these things, energy or momentum.
So the conservation of energy falls out of the doing the calculation.
Yes.
And the conservation of momentum, same thing.
Yeah.
And the conservation.
Yeah. Now we did some examples. I show you how integrating the vertex over all time conserves energy. How integrating it over all space conserves momentum. Same thing is true here. Integrating the position of these vertices and the endpoints of these things over all possible positions in space and time will simply add up to 0 unless energy and momentum is conserved. But apart from the conservation laws, everything that you can draw down will happen with some probability. Right. Now, how could it possibly be that you add up this humongous thing and the answer doesn't come out infinite? Well, the answer is that there are coefficients here. There are coefficients here. These are called coupling constants, particularly the coefficients for the higher powers here. We could call this G3, we could call this G4. And the rule is, in a diagram, in a Feynman diagram like this, every time you have a vertex, let's say with 3 particles coming together, the amplitude contains a factor of G, G3 in this case. So the more complicated the diagram gets, the more powers of G that it has. Each vertex gives you a power of G. If G is a small number, then each successive power of G gives you a smaller and smaller contribution, and you have a chance that the thing might be able to converge. The technical question of whether it really converges or not is a very difficult one, but you can see that you have a chance if G is a small number. If these coupling constants are small numbers, then the simpler the process is, in other words, the fewer number of vertices, the bigger the contribution, and the larger the number of vertices, the more complicated, the smaller the contribution, and you have a chance, at any rate, at some sort of convergence to an answer. If the coupling constants are large, it means these series do not converge, and if they don't converge, it doesn't mean that the theory is wrong. It just means you've chosen a naive prescription for trying to work with it. But in practice, most of the quantum field theory, most of the things we do with quantum field theory are based on the assumption of small coupling constants. And under those circumstances, it's possible to evaluate these Feynman, not just evaluate them, but add them up and find out that the one with 4 vertices is much smaller than the one with 2 vertices. So that's the name of the game.
Do we do color theory in the same way?
Yeah, we're going to talk about color theory. Now the next step is to write down the list of all particles and to write down either in the form of Lagrangians or in the form of Feynman rules. The Feynman rules and the Lagrangians have the same information in them. 3 identical particles coming together, let's say 3 bosons, that's phi cubed. Particles going from one point to another, those are the kinetic terms, the quadratic terms here. So the Feynman type rules and the Lagrangian are the same thing, and you can either describe the world by specifying all the vertices. Incidentally, the lines between one point and another are called propagators. The place where more than 2 particles come together, those are called vertices. Vertices and propagators. All right? But they're, as I said, they're just simply another shorthand way of describing the Lagrangian. The Lagrangian is a shorthand way of describing the graphs. So we would have stated all of particle physics in a kind of dumb way by simply writing down the list of all particles, writing or constructing or even just expressing a quantum field for each particle, and then writing down a Lagrangian for all those particles would contain all of the interactions, or we can write down all of the particles and simply specify what all the possible vertices are. Either way, they come to the same thing. They're kind of a complete list of everything that can happen. Once you know everything that can happen, you can start thinking about calculating amplitudes for particles to go from one place to another, particles to collide and scatter. Here's particles colliding and scatter, 2 electrons colliding and scattering just by a photon jumping from one place to another. All right? Again, the Lagrangian tells you how to calculate the amplitude for each of these. And as I said, it contains all the information, including symmetries, including conservation laws. So I think it's probably, shall we write down the list of all elementary particles?
So when you write down a Feynman diagram, basically the bottom is the initial configuration and
Yeah.
the top is the...
That's right. That's right. The bottom is the initial configuration of particles. The top is the final configuration of particles. And as I said, it is the kind of complementary way to think about field theory, quantum field theory, complementary to the field description, where you would start with a given field configuration and end with a given field configuration. Incidentally, in some sense, the complementarity between particles and fields is very much like the complementarity between momentum and position. These are 2 different ways to describe the same reality, and there are uncertainty relations between them. If you know with precision the number of particles, then you know that there's uncertainty in the values of fields. If you know the values of fields, then there's uncertainty in the number of particles. So these are really 2 complementary ways to describe the same thing, and the Lagrangian is useful in both contexts.
Question. The coupling constants, are those predicted by theory or empirically determined?
Sometimes, under certain circumstances, there are symmetries which relate coupling constants. So this or that coupling constant for this process might, for symmetry reasons, be related to another coupling constant for a different process. So some of them are related to each other by symmetries. But their values in general are simply come from experiment. All right. Much of this, if you really go and learn about quantum field theory, has its beauty. It does have elegance and beauty and so forth. Now when we start writing down the list of facts, what particles there are, what their masses are, what their coupling constants are, it's just a mess. It's just a very ugly mess with very little coherence, except the coherence that comes from symmetries. Symmetries tell you relationships between different kinds of particles and their processes. But apart from the symmetries, which are few and not so much, it is a large number of random facts about a somewhat unmotivated collection of different kinds of particles.
But still, you're pretty confident of the coupling constants because if you change
Once you measure them, you measure them.
if you change it a little bit, then you get wrong answers.
Oh, absolutely. No, I mean, okay, well, let's put it this way. You have too many particles, which means too many fields, too many for any aesthetic sense. You have a lot of them, 100 of them or something, right? A lot of coupling constants, which are just more or less numbers pulled out of an experiment, and a lot of masses, which range all over the map, okay? All right. A few relationships between them, but once you know them, that's it. You can calculate with great precision anything about those particles, and anything about those particles, anything about quarks, electrons, and photons, and so forth, means atomic physics, or it means particle physics, it means atomic physics, it means nuclear physics, it means chemistry, and maybe it means biology, maybe. So the amount of input that goes in is perhaps bigger than you might like, but the amount of output is huge.
Question for electron, for example, how many of the G sub n's would be? G2, G3, G4, would these be calculated?
Or how many G's are there for electrons and photons? In electrodynamics, 1, the electric charge. The electric charge, Well, in a sense, the electric charge is a kind of G3. The electric charge is a kind of G3. The electric charge is the coefficient in the amplitude representing an electron coming in, an electron going out, and a photon being emitted. All right? In terms of symbols, this diagram would be represented by an electron going out, an electron coming in, and the field operator for a photon, which is A. I'm not writing down the details. There are some Dirac matrices, but then the numerical coefficient in front of it is the electric charge in certain units, certain dimensionless definition. All right, now the only processes in quantum electrodynamics are the emission and absorption of photons from electrons. That's all there is. Well, if they're electron collision with a photon, for example. Yeah, electron collision with a photon is just the simplest process would be photon absorbed.
I meant to say proton.
Oh, well, protons are not usually considered a part of quantum electrodynamics. Now, you can think when you do quantum electrodynamics, you are doing atomic physics. You think of the proton as a point, infinitely massive. You don't think of it as something described by quantum field theory. You just think of it as a nailed down heavy particle which never moves until you open up the theory of protons and neutrons. I mean, but, all right, so the scattering by a photon by an electron, this is the first diagram.
But the electron is moving at almost the speed of light relative to the proton?
Proton, yes, but right. Yeah, that's right. Let's draw some diagrams just to get some feel for what kind of things we have to add up. This is the lowest order diagram that goes into the scattering of a photon by an electron. There are 2 powers of the electric charge, so there's an E squared, but this is the amplitude. The amplitude gets squared to find the probability, or the cross-section. Cross-section is another way of speaking about the probability for the scattering. All right? So that means that the whole process, the probability, is proportional to the electric charge to the 4th. The electric charge, at least with a suitable definition, is a small quantity. The square of the electric charge with a suitable definition is about 1. Well, that's the number which is 1 over 137, the fine structure constant. So this is proportional to the square of the fine structure constant. And so scattering in quantum electrodynamics is a unlikely process. A photon comes in and strikes an electron. What is the probability that it goes right through it versus the probability that it really scatters it? The probability that it really scatters it is governed by this e to the fourth, and it's a very small number. Now, we have to add all the processes that we can find, add them up to form a real amplitude. Incidentally, there's another one here which looks like this, where the final photon is emitted before the initial photon is absorbed. That's another process. We have to add them all. But then we start adding more complicated things. Let's focus on here, and we can add another photon. In many ways, this is not the only way. We could have to go from here to here, from here to here. Many photons, but how many powers of electric charge does this have? This has 4 powers of electric charge in the amplitude and 8 in the probability. So this is even weaker. But then we can do even more complicated things. We can put an electron-positron pair in here. Each time we complicate it, we add 2 more powers of electric charge. So in quantum electrodynamics, the expansion is typically an expansion in powers of the square of the electric charge. Every time you add another complicating structure to a Feynman diagram, it's 2 powers of electric charge, and it means it's about a couple of hundred times smaller in amplitude than the previous one. That's why when you add them up, it looks like it converges. Because more and more complicated they get, the weaker the probability from that particular configuration. Incidentally, you don't square this and add it to the square of this and add it to the square of this to find the probability. You add them up and then you square. That's the rule. Add and then square. Add and square. That means there's cross terms between them in calculating the probability. These are called interference terms. So that's the structure of quantum field theory. That's what we do with it. The next issue, as I said, we're now at the stage where we can really start to sensibly talk about particle physics. We can name all the particles. We can specify their masses. Those are the parameters in Lagrangian here that we've spoken of. And we can write down the Lagrangians governing them, partly from theory, partly from experiment, and discuss their symmetries. The symmetries can be discussed by looking at the Lagrangian. We'll do that. And we can write down the standard model of particle physics and discuss some of its properties. So I think we're off to, I think we're set now to move ahead and really discuss the world of genuine real particles and what can be discovered or what can't.
Instead of that m squared, you could have the Higgs field, and then that would be a quadratic.
That's right. And we're going to discuss that. That's right. That's exactly right.
Where are the quadrats?
Where what?
Quadrats, the derivatives. Yeah. Where are they in that expansion?
Oh, they're here. X and X prime could stand for 2 different times. That's how we managed to move vertically.
All right. Which is the term that corresponds to the particle just staying where that's the end?
There's also some terms. No, there are various terms where the particle just stands still. When we wrote down phi of x minus phi of x prime squared, that did have terms in it like phi of x squared and phi of x prime squared. Those are terms where the particle stands still. The cross terms are the ones where it moves. So there are terms where the particle stands still, both from this and from the mass term. Right? Yeah. Okay.
For more, please visit us at stanford.edu.